Well, hello there, yourself. It's Mr. Member here. I hope you're well. I'll apologize in advance that as we go through this video, we might hear a few noises, but that's just because there's a little bit of noise in the background from where I'm sat, but I'll try and explain if any noise is particularly interrupting. Anyway, end of chapter questions, 2 waves. I shall be looking at model answers to questions 5, question 6, and question 7. So we shall be going through those together. Firstly, though, just a few reminder on some tips that you need to be practicing now, but for those of you who have not got a rigor into applying these, I do urge you to do so. So, read the question twice if you can, underline the main parts, keywords, especially very important because the examiner uses very specific language, so words like state and calculate mean very different things. State normally means that you can either infer the value or what is being asked of you, or it's a type of recall question. Calculate means that you will have to apply a formula. Okay, things like describe, discuss, analyze, all those have particular meanings, and those tend to be higher order questions. Okay, quantities, another one very important to underline, making sure that you are aware of what your quantities are under units. So especially where you have sub-multipliers, things like micro, centi, milli, etc., and multipliers, things like mega, kilo, tera, etc. Just make sure that you're aware of those and underline those, and if you have to change it, then that you apply the appropriate standard form. Okay. Where you have to calculate, this is particularly important. I want to remember formula, working answer units, and significant figures. Okay, draw a sketch if necessary. Canolas usually tends to bring the question to life, and as they say, a picture speaks more than 1,000 words. Okay. Look at the allocated marks just to gauge how much time is required, especially in an exam scenario. In this case, of course, if you're going through end of chapter questions, you can take slightly longer than what the timing would be in the exam. Okay, all right. So let's move on to question 1 without further ado. So figure 3 says shows 3 particles. All right. So right away, as I'm reading the question, I can start underlining 3 particles, okay, in a medium that is transmitting a sound wave. Okay, so this is pretty important to know what type of wave is being transmitted. Particles A and C. All right, now we have a sketch here, so we can actually look at the sketch to visualize what's going on, as separated by 1 wavelength. All right, so we can underline that, but it is also in the diagram. And particle B is halfway, so between them, when no sound is being transmitted. Okay, so this is between, so that is the position of B when no sound is transmitted. It's halfway, exactly in that position. All right, so it says name the type. So that's the key word there, name the type of wave that is involved in the transmission of this sound. So, you know, that is a recall question, and this is a longitudinal wave. Okay, it says at one instant, particle A is displaced to the point A dash, indicated by the tip of the arrow in figure 3. Okay, so it's indicated by the arrow. Show in figure 3 the displacements of particles B and C. Okay, and it's the displacements we have been instructed at the same instant. Label, that's another keyword there, label. All right, so the examiner wants us to label them with B prime and C prime or C dash respectively. All right, so there we go, A and C. This is the direction, it's moving towards the right. In this case, I would be, well, let's look at A and C. They're 1 wavelength away, which means if we think about it in terms of phase difference, that they are 2 pi, yes, degrees in radians, or they're 360 degrees, if you like, out of phase, which means essentially that they are oscillating in phase. That's what that means. Okay, so if I just use a diagram here to elucidate the point, so if I've got my wave like so, and between these 2 crests would be my wavelength. Now this here is equivalent, if that was my 0, this would be 2 pi position. Okay, now these points here are in phase or oscillating in the same direction, and the point that's halfway exactly halfway at lambda over 2, we can see is in antiphase, or 180 degrees, or if you want it in radians, you can say pi radians out. Okay, so if we have to draw C, we know that C will be going in the same direction as A, and we denote that the displacements are being denoted by the size of the arrow A to A dash. So therefore, the size of my amplitude of C will be the same size, and that is C dash. Okay. Next part, B. If we look at B, we just said B is halfway. So halfway, okay, so that's B. Now B is halfway, so it's going to be in antiphase, 180 degrees out of phase. So it has to be going in the opposite direction, but with the same amplitude. Okay, so there we go, and we get B, and I label it as B dash, and my answer, or answering that question, is complete. Okay, moving on to the next question. Figure 6, question 6, figure 4, represents a stationary wave on a stretched string. The continuous line shows the position of the string at a particular instant when the displacement is a maximum. Okay, that could be very important information. P and S are the fixed ends of the string. Q and R are the positions of the nodes. Alright, so there are our nodes. The speed of the waves on the string is 200 meters per second. Okay, speed of the waves, 200 meters per second, inclusive of the unit. We have to pay attention to that. So it says state the wavelength of the waves on the string. Okay, keyword here is state. So we can actually infer this from the diagram without really having to engage ourselves in a lot of calculation if we wanted. Okay, so we can see here by looking at this figure that the distance between this node at the wall to this second node here would represent a wavelength. Well, look at, or in other words, if I look at each of these eyes, each of this loop, this represents half a wavelength, so to speak. Okay, if I get two of these halves, I get a full wavelength. Now I've got 1, 2, 3, meaning I've got 1.5 wavelengths. Okay, 1.5 wavelengths. Or in other words, what I could do is find the length of each of these loops. So I've got 3 of them, so 1.2 divided by 3, so I know that each one would be 0.4. That point P, okay, alright, I'll repeat that. From this point P to this point R, we have 2 out of 3 loops of 120, so I can work that out as being 0.8 meters. Okay, so just repeating this again differently. The spacing between two nodes, we do have a node at the wall that represents lambda over 2, so plus lambda over 2 plus another lambda over 2. That's what I've got there. Okay, so these two would make lambda. So if I've got 3 of them, 1.2 divided by 3 of them, that gives me 0.4, which means that each of these is 0.4 to there, 0.4. So the total wavelength would be 0.8. So there we go, 0.80 meters. Now it's to the right number of significant figures as well, looking at the data given. Next part says calculate the frequency. I'll have to take this out. Okay. Calculate the frequency of vibration. Okay, calculate is the keyword, and it's the frequency. So now frequency is measured in hertz, so I will simply do part B here. So we say speed is frequency times wavelength. Therefore, we know that the frequency is the speed divided by the wavelength. We have been told the speed is 200. The wavelength is 0.8. Therefore, we get a frequency of 250 hertz. Okay. Draw on a copy of the diagram of the diagram. So draw on a copy of the diagram the position of the string, so the position 3 milliseconds later than the position shown. Okay. Finally, explain how you arrive at your answer. So draw, so we're going to have to sketch something on the diagram given. Okay, now it says 3 milliseconds later. We know what the frequency is, and we know, using my cursor here, that in one time period, this bold line will firstly drop and take the shape of the dotted line in its, if you like, it will invert in half a time period, and it will then return back to its original position in a full time period. Okay, so that's the key thing to note. So if we know what the frequency is, we can apply the formula F equals 1 over T. Rearrange it, or if you're already at T equals to 1 over F, then that's even better. So we get 1 over 250, which gives us 4.0 times 10 to the minus 3 seconds, which is equal to 4.0 milliseconds. All right. So it takes 4 milliseconds to go from that bold shape into the dotted shape and then back to that bold shape. In other words, to return back to this original snapshot we have. So we can tell that to go from there, from the bold line into the dotted line, that'll be half a time period. So if I started my clock, and that's my time equals to 0, I know that I'll achieve this shape in a time that is half the time period, which is T equals 2 over 2. Okay. When I now get back to this top, this time it will be a full time period. So let's think then. So what is 3 milliseconds as a fraction of 4 milliseconds? So it means I will be 75% halfway through my cycle. So this is 50% at the bottom. So 75% means that my line here would now be there, and I'll be in the undisturbed position. So I know therefore that if I drew a line, it will be a flat line, because at this point my time is 3t over 4. That represents 3t over 4, or 3/4 of the time period. So therefore, in explaining it, say 3 milliseconds is 3/4 of time period. Okay? And therefore, wave will be in undisturbed position. Oops. Undisturbed position. Okay? So we calculated the time period and then used that to say that 3 milliseconds is 3/4 of the full time period. So let's just look at where the marks are coming from in this one, especially because it doesn't quite split them up. So the first one, it's 1 mark stating it. Calculate the frequency, that's another mark. Okay. Drawing on the graph, that's another mark, and then 2 marks. You calculate your 4 milliseconds. You show that it is 3/4 of the time period, and therefore will be in the undisturbed position. Okay, right. Next part then, question number 7. Short pulses of sound are reflected from the wall of a building 18 meters. So short pulses just underline a few keywords. Short pulses, reflected, okay, from the wall of the building, 18 meters from a sound source. The reflected pulses return to the source after 0.11 seconds. First part says calculate the speed of sound. Now this is where a quick sketch, can't do any harm. So that's my pulse. Send forward. And I also get a pulse that returns back like so. The distance between the source we instructed is 18 meters. Calculate the speed of sound. So we know that t is equal to 0.11 seconds, and we already have a value for a distance. So applying speed equals distance over time would yield. Now let's think very carefully. The distance is 18. That's only to one direction, but because it's gone to and fro, the distance it's traveled in 0.11 seconds is actually 18 meters times 2, so 36 meters. Okay, should close it off with a double line. It's 36 meters. Okay, so distance 36 divided by time 0.11, and we get a value of the speed as 330 meters per second. Two significant figures, which is what our values are given in. Part B, that's part A. Part B, sound source now emits a continuous tone. So it's not short pulses anymore, it's a continuous tone at a constant frequency. Okay, an observer walking at a constant speed from the source to the wall here's a regular rise and fall in the intensity. So we know it must be because of the formation of stationary waves here. Now it says explain how the minima of intensity occur. Okay. So as we said already, we know that in this case we now have a continuous pulse like so, and we've therefore got points called nodes where we'd be expecting that drop in the intensity, and positions which we call antinodes where we would be experiencing a rise in the intensity. So this is explain, then we've got to explain how the minima, so we're interested in explaining how these nodes arise. Okay, so the key thing to state here, you want to be using key scientific terminology when explaining how this is actually formed. So what you want to say is, firstly, you want to state that a stationary wave is formed in the air. That's the medium he's walking in. Okay. By the superpositioning of the incident and reflected wave. Okay. At points where there is a fall in intensity, meaning where we experience the minima, destructive interference occurs. As running out of space here, the waves are in antiphase, or they're 180 degrees out of phase. Okay, so here we go. Just to look at where the marks are coming from. So for the first part, making sure that you use the right formula, but also you don't get caught out with the distance. You use the distance as 36 meters. Okay, so a final value with the right significant figures comes out as 330 meters per second. The next part, so you have to mention the fact that a stationary wave is formed. First mark. It's formed by the superpositioning of the incident and reflected sound wave. Second mark. At the points where there is a fall in intensity, meaning the minima, destructive interference occurs as the waves are in antiphase. Okay, and those are the model answers, folks. Actually, completeness sake, don't think I showed you where the full marks are coming from here, but there we go. That would be your 1 mark, and this here would be your, let's get that right, this is 2 marks, so 1 mark for each of those points. Thank you.